In this question, we are required to show that f of x is equals to cos x is equal to its Maclaurin series expansion and find the radius of convergence. Now, so for A, its Maclaurin series, the Maclaurin series expansion of cos x is 1 minus x squared over 2 factorial. We've already shown this in the previous example, so I'm not going to go through it again. Plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial minus plus x to the power 8 over 8 factorial. Now, this series goes up to this nth term. Now, let's look at powers of -1. That will just be to power n, because this is n to power 0, n to power 1, n to power 2, and then x to power 2n over 2n. So we've already looked at this. All right. Just checking that I wrote it properly. Okay, good. So let's carry on. What do they want? They want us to find, to show that it's equal to its Maclaurin series expansion, which means we have to show that the limit of the remainder term will be equal to 0 as n approaches infinity. All right. So basically, we need to show that so what you're going to do is write an expression for the remainder term. So the remainder term is given by the n plus 1 derivative of f at z multiplied by x minus c to power n plus 1 over n plus 1 factorial. And we know that for this particular series, the absolute value of the n plus 1 derivative at z will be less than or equal to 1. Because it's cos x, nth derivative of cos x will just be either sine x or cos x, and the maximum, those values are less than or equal to 1, the values of sine x or cos x at any value of z. So, and we know that c is equals to 0, which means what I'm going to do is I'm just going to plug these guys here, all right, this point and at this point, which makes my expression for the remainder term much easier. So anyway, what I'll have is the remainder will be equal to the absolute value of x to power n plus 1 over n plus 1 factorial. And we have already shown in the previous videos that the limit of this will be equal to 0 as n approaches infinity. So I'm not going to go through all those steps again and again. So what we'll just say is that hence cos x will be equal to the sum from n is equals to 0 to infinity of -1 to power n x to power 2n over 2n factorial for all values of x. Now, if this series converges for all values of x, then the radius of convergence will just be infinite. All right, we discussed that when we looked at power series. Good. I'll move on to B. Now for B, they want us to find the Maclaurin series expansions for the following, including the radius of convergence. So we know that cos x is equal to the sum from n is equals to 0 to infinity of -1 to power n x to power 2n over 2n factorial. So we can say that cos 2x will be equal to so cos 2x will be equal to the sum from n is equals to 0 to infinity of -1 to power n. Now in place of plugging in x, we'll plug in 2x, so that will be 2x to power 2n over 2n factorial. And the radius of convergence will still be the same. So the radius of convergence will be infinite. I believe that's what the question is asking. All right. And then the next question is, so this is part B1. B2, hence find the Maclaurin's series expansion for sin x. So we have cos x, and we know that the interval of convergence is infinite. So what we can do is we can integrate. So we can say, since radius of convergence or interval of convergence we can integrate. Now we know that if you integrate cos x, you end up with sin x. So basically, we can go ahead and perform that. Now we know that sin x is equals to the integral. So we can create an integral here with the limits 0 to x of cos t, because we know that if we integrate cos t, we'll end up with sin x. But fortunately for us, we have an expression for the summation. We have an expression for cos t up here, because x is that. So basically, cos t will be given by this will be the integral from 0 to x of the sum from n is equals to 0 to infinite of -1 to power -1 to power n t to power 2n over 2n factorial dt. All right. So basically what I've done here is that bit has been replaced by that bit, okay, which comes from this bit here. All right. This bit. Or actually, it's the whole of this bit. So the whole of this bit has been plugged in here. All right, anyway, I'm going to carry on. So we need to integrate this guy. So this will be equal to, we can move the integral sign inside the summation sign and factor out things that we can't, that are constants. So negative 1 to power n over 2n factorial, and then we have our integral 0 to x t to power 2n dt. And then we can just go ahead and integrate that, which will be equal to the sum from n is equals to 0 to infinite, negative 1 to power n over 2n factorial. And this will be equal to t 2n plus 1 over 2n plus 1 x0. Okay, just checking that everything is written. So this will be the sum from n is equals to 0 to infinite, and that will be negative 1 to power n over 2n factorial, and this will be x to power 2n plus 1 over 2n plus 1, because if you plug in 0, then it's all gone. That would just be minus 0. So we can simplify this to be the sum from n is equals to 0 to infinite of negative 1 to power n x to power 2n plus 1 over 2n plus 1 factorial. Okay, and the radius of convergence is infinite, same as the original series. All right.